Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over orbital diagrams regarding molecular orbital theory and molecular orbitals, and we're going to talk a little bit about electron configurations involving molecular orbitals. So let's get into this. So in my previous video, I showed you the orbital diagram for hydrogen. So now in this video, I want to kind of show you other orbital diagrams, but I want to talk about bond order and show you how you could use orbital diagrams to predict what the bond order or how many bonds are going to be forming between certain atoms. Okay, so here's H2 again. And so again, so when you're filling in your orbital diagram, I just want to remind you about the diagram. So the orbitals on the outside are the atomic orbitals from the atoms. So here we have hydrogen atomic orbitals. So the 1s orbital from this hydrogen, the 1s orbital from this hydrogen. So separately they have their atomic orbitals, but when they come together, form a molecule, then you're going to get the molecular orbitals due to the linear combination of atomic orbitals, LCOA, okay, or LCAO, sorry. So each hydrogen atom has one electron, right? So we're going to put the electrons into the atomic orbitals. And remember, when the electrons interact, when the wave functions, right? If we treat each electron as a wave function, they're going to interact in two different ways. They're either going to interact constructively to form a bonding sigma 1s molecular orbital, or a non-bonding or anti-bonding sigma 1s star. So here's the two molecular orbitals for the hydrogen. I should put MOs here for molecular orbitals. So the molecular orbitals are in the middle. And then what we do is we take the two electrons here, or any electrons, the valence electrons that are in the atomic orbitals, we're going to put those and start filling in the energy diagram for the molecular orbitals. And it follows the same strategy as filling in your atomic orbitals. Remember, when you're filling in your 1s2 with two electrons, and then your 2s, and then your 2p, and then your 3s, and so on, you follow the Aufbau principle, right? So you fill in the lower energy levels first, and you start there and you move all the way up until you run out of electrons to fill in. You follow the Pauli exclusion principle, which means that you only have two electrons in each orbital maximum, and they have to be opposite spin. So one is spin up, the other is spin down. And finally, you have Hund's rule, where if you have energy levels, or if you have orbitals that are at the same energy, then you fill in one at a time with the same spin before pairing them up. So we're going to follow those same rules when we're filling in our orbital diagram for molecular orbitals. Okay, so here's the hydrogen. So the two electrons are going to come together. We're going to fill in the lowest energy level here first. So this is the sigma 1s molecular orbital, gets filled in first with two electrons. And so now that is full. And so that's it. So we don't have any more electrons. And just like with your atoms, you can write out your electron configuration according to the orbital diagram. You also have electron configurations for molecular orbitals. So for your H2, the molecule, the electron configuration for the molecule H2, we're going to use the molecular orbitals starting from the lowest energy, working our way up. Since we only have two electrons in this molecular orbital, then the electron configuration for H2 is just going to be the sigma 1s with two electrons, right? So you want to put brackets around here, and then we put 2 there. So we have our molecular orbital, and the 2 there indicates that we have 2 electrons in that orbital. So this would be the electron configuration for the H2 molecule. Okay, now notice, okay, we can calculate the bond order. So calculating bond order. Now, when we're talking about Lewis dot structures or valence bond theory, the way that you calculated bond order was you counted the number of electron pairs that were shared between the two atoms. So if you had one electron pair, which means two electrons, if you had one electron pair, that was a bond order of 1. If you had 2 electron pairs or 4 electrons, that would be a bond order of 2. If you had 3 electron pairs or 6 electrons, that would be a bond order of 3. So you counted bond orders by the number of electron pairs shared by the atoms. Now, if you had resonance structures, right, if you had resonance structures where the double bond can move according to different electron structures or different resonance structures, then the way you figured out bond order is you counted the number of bonds and then you divided the number of bonds by the number of atoms that were bonded to the central atom or that was sharing that double bond, right? So that way you could get 1.5 bond order or 2.5 bond order or 1 1/3 bond order. The way you figure out bond order using molecular orbital theory is this equation here. So the bond order is going to be the number of bonding electrons minus the number of anti-bonding electrons, all divided by 2. So what does that mean? The number of bonding electrons are the electrons that you have in bonding orbitals, right? So here we have 2 electrons in our sigma 1s. There's no star there, so this is a bonding orbital. And then you also have your anti-bonding orbitals. And so the number of anti-bonding electrons is the number of electrons that you find or count in your anti-bonding molecular orbitals. So you're basically going to subtract out the number of anti-bonding electrons from the number of bonding electrons. And so, and then once you get that difference, you're going to divide by 2, and that's going to give you the bond order. So if I apply that here, the bonding order BO, it's equal to the number of bonding electrons. So we have 2 electrons in the sigma 1s, which is a bonding molecular orbital. So we're going to take the 2 electrons, and we're going to subtract out the number of anti-bonding electrons. The 2 electrons is all we have, so there's nothing up here above. So we don't have any electrons in any anti-bonding molecular orbitals. Here we have the sigma 1s star. That is an anti-bonding orbital, but there's no electrons in it. So that's going to be subtracting 0. We divide that by 2. So that's going to be equal to 2 over 2, which is equal to 1. So we have a bond order of 1 for the H2 molecule. This fits really well with the fact that we know that hydrogen has a single bond. So we got that from the Lewis structure, our Lewis valence bonding pairing of electrons idea or theory, where we pair electrons to get our single bond. And so the bond order from molecular orbital theory fits. So as we said before, the hydrogen has a bond order of 1. It's a single bond. And so this is because the 2 electrons are filling in your bonding orbital, your molecular orbital here. And notice that this molecular orbital is lower in energy than the 2 separate atomic orbitals. So this is much more favorable. So this molecule readily forms when you have 2 atoms of hydrogen that are going to bond together. Okay, now we could do this with other combinations. We could do this with we can do this with ions and other molecules. So if we, instead of having hydrogen plus hydrogen, we could change one of these to an ion. So this would be an H plus ion. So that means that this H plus indicates that it lost an electron. So this hydrogen, this H plus ion, doesn't have any electrons because we took it away. This hydrogen has one electron. So that means that this atomic orbital only has one electron. I'm sorry, this molecular orbital only has one electron in it. And so if you have an atom of hydrogen plus an ion of hydrogen, those are going to come together to form H2 plus with a charge on it. So this is what the orbital diagram would look like for H2s. If we calculate the bond order of H2 plus, in this case, we have one electron in the bonding orbital, so that'd be 1. We still don't have any electrons in the antibonding orbital, so that's 0 antibonding electrons. So subtract out 0, and we're going to divide that by 2. So we get 1 over 2. So we get a bond order of 1/2, which means that the bond here is going to be less stable than the having the 2 electrons in here. So the bond order is lower, meaning that this bond is not going to be quite a single bond. It's going to be less than a single bond. So if you look at the data for H2 plus, you'll find that the bond for H2 plus is a little bit longer than that of H2. And also it's a weaker bond. You'll find that the bond energy is weaker for H2 plus compared to just the H2 molecule with no charge on it at all. And so the bonding order that we get from the molecular orbital diagram fits nicely with the data. Now, what about helium? Now, if we do helium, let's do He plus. So instead of hydrogen, we'll do helium. So let's say we have helium. Helium only has a 1s orbital filled with electrons. And then also the same thing on this side. We'll have helium here. And we'll make this He plus. So we have an ion bonding with an atom, and then that's going to form the He2 plus molecular orbitals. Oh, and I forgot. So for the He, so this is the electron configuration for H2, the molecule H2. The electron configuration for H2 plus would be sigma 1s, and it has one electron in there. So that would be the electron configuration for H2 plus using the molecular orbitals. Okay, so back to He2 plus. So in this case, both helium, this helium has 2 electrons in the 1s orbital, so spin up, spin down. But since this has a plus charge on it, it lost 1 electron, so this has only 1 electron left. So spin up. So now we're going to take the 3 electrons and we're going to fill in the orbital diagram from the lowest energy molecular orbital to the highest energy molecular orbital that we can fill. So since we have 3 electrons, again, following the Aufbau principle, we're going to start with the lowest energy. Pauli exclusion principle says that the molecular orbital can hold a maximum of 2 electrons, and they both have to have opposite spin. So we're going to take 2 electrons, put them here, spin up, spin down. So that's 2. We got one more. We can't put it there because this orbital, this molecular orbital is full. So we got to go to the next higher level, which is the antibonding molecular orbital, sigma 1s star. So we're going to put the electron up there. And so you'll notice here that we have our orbital diagram filled in. And so now we can calculate the bond order. So for the bond order for helium plus He2 plus, we have 2 bonding electrons, so that's going to be 2. We now have 1 electron in the sigma 1s star, which is an antibonding molecular orbital. So that's 1 electron or 1 antibonding electron. And so now that's going to be divided by 2. 2 minus 1 is 1, divided by 2 gives us 1/2. So we have a bond order of 1/2. And so this is going to have a something less than a single bond. So relatively weak bond here, but a bond nonetheless. So He2 plus is a possible molecule that can form with 2 helium atoms, one being an ion, one being a neutral atom. So it does have a bond between the 2 atoms, but that bond is a half. It's going to be a weak bond. And so that's going to be impossible. So again, if we write the electron configuration for helium 2 plus, this is a molecule. So the molecular electron configuration is, we again start with the lowest energy molecular orbital and work your way up until you go through all the orbitals, just like any other electron configuration. So you start with the sigma 1s that has 2 electrons, and then you follow that by the sigma 1s star, and that has 1 electron. So that is the electron configuration of the He2 plus molecule using your molecular orbital diagram. Okay, one more. What about He2? So instead of the plus, what about He2? Is that possible? So in this case, we have 2 electrons in this helium. Now we have 2 electrons in that one. So now we have 4 electrons that we have to fill in our molecular orbital diagram with. So again, we're going to have 2 electrons in the 1s, in the sigma 1s bonding molecular orbital. But this time we have 2 more electrons, and we're going to fill in the antibonding orbital with 2 electrons. So the 4 electrons in the atomic orbitals are now filling in the molecular orbitals in the middle. So now we have 2 electrons in the bonding sigma 1s, and we have 2 electrons in the anti-bonding sigma 1s star. So let's calculate the bond order of this possible molecule. So we have 2 antibonding. We have 2 bonding. We're going to subtract out the 2 antibonding, and we're going to divide that by 2. 2 minus 2 is 0, divided by 2 is 0. So this has a bond order of 0, which means basically there is no bond. So this is not, oops, I forgot to change that to He2. So He2 is not a possible molecule. And so we would know that because, of course, from previous learning, from my previous videos, we know that noble gases are stable. They don't like to form bonds. They don't form molecules except for under certain circumstances for some of them. But by and large, you're not going to form molecules of noble gases. So it's not surprising that we would find out from the molecular orbital diagram that He2 is not a possible molecule. and the bond order tells us that from the molecular orbital diagram. And so what this kind of shows us, and I said this before in my previous video, is that remember, your bonding molecular orbitals have a stabilizing effect. So this lower in energy. So these electrons want to go into lower energy. So if you can form a bond and therefore fill in the molecular orbital for the molecule, that's going to stabilize the bond and stabilize the molecule, right? However, the anti-bonding molecular orbital has a destabilizing effect. So if you fill in the molecular orbital, that's going to stabilize the bond in the molecule. But if you start to fill in the anti-bonding molecular orbital, that's going to destabilize that bond. And so, as you can see here, the two electrons here are canceled out. The stabilizing effect of the two electrons in this molecular orbital are canceled out by the destabilizing effect by the two electrons here, therefore giving you a zero bond order, or in other words, no bond. So that's a really important thing to keep in mind when you're thinking about the stabilizing and destabilizing effect of your molecular orbitals, your bonding molecular orbitals, and your anti-bonding molecular orbitals. So anytime you have an equal number of bonding and anti-bonding electrons, you're not going to have any bonds. That's not going to form any molecule between those two atoms. Okay, so the other thing I want to point out here before finishing up is that, well, the next thing, the electron configuration for He2, if it was to form, would be sigma 1s2 and then sigma 1s star 2. But of course, that's not going to form because it has a bond order of 0. The other thing I want to talk about is the fact that the molecular orbital theory can, not only does it help explain or give the results that we saw from previous theories like valence bond theory, where you can get a single bond or triple bond or double bond in your molecule between certain atoms, but also it helps accommodate and explain, or I should say support the idea or explain the idea of having odd number of electrons. So when you draw your Lewis dot structure, you almost always have lone pairs. You always have an even number of electrons. Not always. There are things called radicals that have an odd number of electrons, and sometimes you run into those in your Lewis dot structure. But most of the time, they're even number of electrons. Also, in your Lewis dot structures or in your valence bond theory, you're always pairing up single electrons, so you always end up with a pair of electrons. But molecular orbital theory is able to accommodate and explain very, very easily odd number of electrons. So when we had only the He plus, right, He2 plus, we had an odd number of electrons here, and it was able to explain our bond order of having 1/2 bond order. And so that's something that the molecular orbital theory can help explain much better than the other things that we have looked at. So I hope this is helpful with the bond order and the orbital diagram and the electron configurations for molecules. If this was helpful in any way, if you enjoyed this video, then by all means like the video, share the video, hit that like button somewhere on the bottom here. Also, do me a favor, subscribe to the channel if you haven't already. Click that notification bell. When you do that, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask some questions. I would love to hear from you. If you have a question or a comment, put that down below. If you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me, and have a great day.